Well, I think we can start officially. Welcome back, everyone. So we are pretty much where everyone wants to be in a calculus class. Week 15, we're just about done. In week 15, I decided not to pursue any further sections. I think 10.2 is going to make the best capstone section for this class instead of trying to push forward, mainly because section 10.3 in our book is exclusively polar coordinates. The calculus is in section 10.4. I don't think we have enough time to really kind of cram all that material in at the very end. So we're going to finish on section 10.2. This is our last official section and last official assignment, so that's kind of awesome. Then once we finish the example there, we'll move on to the final exam review problems in this document here. As we go through these, if you have other questions you'd like to bring up, whether they're from other review documents, other homework problems, or just other random questions from the textbook or otherwise, don't hesitate to interject. We don't have to do these problems in order. We can jump around during our review. But we'll finish off 10.2, begin working through this document, and we'll probably be coming back to the problems on that document on Wednesday's review and Thursday's review as well. So pretty much we're just reviewing early for the final exam. Aside from the other announcements, we have the extra credit opportunity for the course evaluation. This one has a firm deadline on Friday, December 6th, because the math department closes all of their online course evaluations for every single math class in this department on that date. So to get the extra credit, what will happen is we'll have a total of 3 homework assignments dropped by submitting that evaluation and showing me the screenshot just of the completion page. Other extra credit opportunities relative to the final exam. And so that's pretty much the announcements for this week here. Any questions, comments, or concerns or anything like that so far? Okay, well, the further announcements, we'll probably rehash a couple of these things when we're on Wednesday's review and Thursday's review, here's the more expanded information for the final exam. I put down here kind of a breakdown of how I'm selecting questions, because honestly, that's usually something that's kind of scary about a final exam. When you say it's comprehensive over all topics, this is what I mean specifically. This is how I'll answer those questions. So there'll be quite a lot of stuff we did in chapter 7 on integration techniques. Not too much in chapter 8 on, this was applications. Chapter 9 was differential equations. A big part of the course was chapter 11. But it looks like we're only going to be dealing with 6 questions in total from those sections specifically. So one question is going to be deriving a Taylor series or a Maclaurin series from section 11.10. So that's really 11.10 part 1 we're emphasizing more. Then one question from section 10.2, that's the last section that we're doing right here. The question I'm going to ask is going to be a question that's both been asked on the 10.2 lecture notes and on the homework assignment. My goal is to make it pretty similar to what you're doing on this homework assignment, because it is the last section. It's hard to really get great feedback on that. But if you get this to me before the due date, I'll grade these as soon as I can to try and get it emailed back to you before the actual final exam on Monday, December 9th. Well, any questions so far? Okay. Other thing about the final exam is, let me see what I wrote here. Okay, just double checking. I have different exam policies in all my classes, so I get paranoid that they might overlap. One of my classes does not have page of notes allowed on their exam, but we do. Don't forget we have a single 8.5 by 11-inch page of notes, handwritten. Don't forget a calculator as well. And before you go to make your page of notes, this document says, read this. This is the real last page of the actual final exam, which has already been printed, so nothing can be changed at this point. So the last page is going to have all the tests for convergence and divergence. So that clears up a lot of real estate on what you'd probably put on your page of notes for the exam. You might decide to leave off this information here. Also has a nice little trig table at the very bottom, since we get used to seeing that. And there'll be a couple problems where we'll need to make use of that, not a ton. So when you go to create your page of notes, be aware that this is going to be the real last page, and you can even tear it off on the last page and use the back for scratch paper, like on the rest of the exams. And there's more new documents here as well. Sample exam version 1 are the same problems that you've been looking at, but it's been expanded all the way down to section 10.2 now. When it says some are very challenging problems, those are just there for extra rigorous practice. They are not actual challenge questions that would be on a real final exam. This is probably a more valuable review document for the purposes of being prepared for the final exam. Version 2 is blanked out lecture notes. The way you work this is just pick a section you feel like you need extra practice in. Maybe it's 7.4, approximate integration. What I did is I took out essentially everything but the problems. So this is now just a worksheet really, where you can try out the problems. And then you can go back to section 7.7. That was way up there. There it is. And go back to the examples to check your work and see how you did. We might find a typo in there. So if you see an actual mistake that was left in, let me know and we'll get it corrected right away. So that's how to work the second version of the final exam. So the second version is all the lecture notes with all the formulas taken out. So it feels like you're really studying for a real exam. You're not distracted by all this extra information. Or I was supposed to be highlighting that one. That's the one with the lecture notes. I put here for version 3 that real final exam questions are most similar to these. They're pretty similar to these ones. These are a little bit more challenging, but these are the most similar final exam questions. If you open these up and you feel like you're looking at something that's kind of deja vu, it's because these are all of the homework questions of the entire course. In fact, when I go to write a final exam, I pull up a document like this one, I pull up a document like this one, and I go section by section. And I look at what did we actually do as a class for the homework? What did we do for a class in the lecture? And I motivate what I write as a final exam question based off these two documents. So anything that was a homework question or a lecture note question is a good candidate for a real final exam question. And you can check these as well, since these are graded assignments. They're primarily odd questions, so you can go back to the exercises they came in and check the odd answers for solutions to see how you're doing on those problems currently. Honestly, they're just as good as they were before because I don't think anyone memorizes all hundreds of problems that's on this document. The last set of review documents are exams 1, 2, and 3. Be careful with these though, because you have to be aware exam 3 only went to section 10.6. So it's of limited value for everything beyond that. However, if you want to just review what happened on exam 1, exam 2, for example, or exam 3, flip one of these random documents and set like a timer, 70-minute timer, and just run through this exam question as if it was a real, legitimate, honest exam. If you have your old page of notes that you used on this exam, might as well pull that out as well. And they'll tell you how you're doing on that content. Then you can grade your work by just going, Moodle website is just a giant document, resource document now. The solutions to all the exams are posted somewhere at the very bottom. Usually it's the last document in the exam information. So that fills out the full set of review materials. These are really specifically for you, but if there's any problems anywhere in here you'd like to see done, as we go through this review document, again, don't hesitate to interject. I'll be happy to take a look at that question. So that's our goal so far. We'll work through section 10.2 and then jump into the review. And this is where we left off right before the long break. Probably want to take a look at some of this again, see what we were doing. Any questions at all, folks, before we get started in earnest? Okay, looks like we can start. So section 10.2 had 2 questions left over. Because we're just about done with the course, this is a good question right here to do because it's a real homework question, which means it could be a legitimate final exam question. I propose we skip this one. It's not on the homework assignment. It's not a question I'm going to ask on the real final exam. If you're curious on how this one goes, really similar to example 6, but the integration on this thing is pretty tough. So I'm happy to come back to this one if folks would like to. I propose we hit example 6 and then move into reviewing for the final exam. Does that sound all right to folks? Okay, so this is, again, the last question that you'll see on the homework assignment, the last one. It says the position of a high energy proton in a large hadron collider is given by this information. So we know it's positioned parametrically this way. on a time interval from 0 to 1 femtoseconds, so that time interval. Distances are measured in femtometers, so 10 to the power negative 15 meters. And we just want to know, how far did this particle go from 0 to 1 femtoseconds? That might be a pretty important problem, but I don't know enough physics to tell you that. But this is a pretty, at least the units are right for this kind of problem. To make this happen, we're just going to take the length of this parametric curve. It's specified this way. We take dx dt, square it. Same for dy dt, take the summation and the square root. It's really derived from this right here, our ordinary length formula. We're mentioning this because this is good final exam review as well from section 8.1. But the change is when we go to make the differential out of x equals f of t, using the change of variables here, you can now do a bit of algebra and show that it becomes this equation here. You know, it's kind of nice in a way. You just take the x derivative, the y derivative, square root, and move on. So let's try it out on this one here. Probably want a new page though. And maybe before we do anything at all, when it comes to parametric curves, it's always a good idea to just get a lay for the land, see what's going on. Because we discussed a good amount on this one. When you're going to find the length of a curve parametrically, you want to first ensure this curve is only traced out once as a parameter increases from 0 to 1. If I put down a random problem on paper, that may or may not be true. We have to check it out. So let's check it out then. I mean, if this is a real final exam question, you could assume that it was written in a way that you don't have to use extra technology to determine if it's a legitimate problem. But to plot these, you just start with the parenthesis, put in the x-coordinate, 2t squared. See if I remember how to do this. The y-coordinate, 3t cubed. You go down here, and usually you can put 0 to 1. Well, let's go A, type in A, B, add a slider for both. A is going to be the lower bound, the lower limit of integration if you're thinking of an integral problem. So it's going to be set to 0. B should also be set to 0. We imagine B increases as it goes up to the upper bound on the parameter, up to 1. So as B increases, looks like this is the way the curve is being swept out. Oh, I zoomed out too much. So from 0 to 1, looks like it's only being swept out in one direction, never doubles back. So when we go to find the length of this curve, we really are integrating from 0 to 1. We will get its true length. So there it is. There's our curve that we're trying to track its motion of. First thing we ought to do is, oh geez, that's a cool way to taste, I guess. But the first thing we ought to do is a bit of algebra. Go to x and calculate dx dt. So this is the relaxing part of the problem. You'll get 4t. Move over to the y-coordinate and do the same. dy dt is now 9t squared. And the formula says you have to square both of these. Might as well just do it right here. You know, maybe not. That looks like it's getting a little too busy. I'll do it on a line down below. So dx dt squared plus dy dt squared. So the next thing we'll calculate. We also have to square root it. So in this problem, the square of this is going to give us 16t squared. Plus, square of this one gives us 81t power 4. And this is our integrand. We need to integrate that thing from 0 to 1. Does it look super friendly, but algebra can help us out because you can rewrite this as square root t squared times square root 16 plus 81t squared. And that helps out a little bit. Can go even further because the square root of t squared is not the absolute value of t because t is non-negative. So we can simplify and say that this equals t root 16 plus 81 t squared. So that's our integrand. Really, the only thing we need to do now is integrate that from a lower limit of 0 to an upper limit of 1. Any questions to this stage so far? Okay, let's see how this comes out. So the length of this path, or the distance that was traveled by that particle, is going to be, let's actually call it distance. It kind of matches with the problem a little bit better. The distance is going to be the integral from 0 to 1 of t root 16 plus 81 t squared. So we drop our result of this thing right here, and all we now need to do is integrate that function. That's not too bad of an integral. If you've got power 2 as an inner function inside the square root and power 1, that suggests a u substitution should work pretty well for us. So let's take all of that and call it u. U is now 16 plus 81 t squared. Next thing we need is its differential. So du would be 162 t dt. The t dt is what we need to make the u substitution work, since we have now a match here and here. But if you like, we can divide out the 162. I think that's what our author usually does in this situation. So we have 1 over 162 du equals t dt. So much of this calculus we've been working on is just clever rearrangement of differentials. And that's pretty much all we're doing right here. T dt becomes all of this. We'll swap out the limits of integration as well. We have t equaling 1 down to 0. We're plugging that into the u substitution right here. So when it's 1, we're going to get 16 plus 81. So 97. When it's 0, we just get 16. So now we're ready to swap out for a better integral. This one goes, first let's write out, go from 16 to 97. Highlighted in yellow, we're putting in 162 in the denominator, du. So that takes care of the yellow portion. And here we just have u to power 1/2. So we've now transformed this integral to early calculus 1 integral. This one is just a matter of running through the motions now. So first, let's write out 160 seconds.
You wrote a 92 instead of 97 on the interval.
Oh, good call on that one. I was never going to spot that. Thanks for spotting that. Goes to 97, and I dropped that by 5 for some reason. 97 there as well. Other questions at the moment or comments? Okay, thanks for spotting that one. So at 97, next, this goes up to power 3/2, which means we multiply by 2/3. Parentheses here is just a way to say, I'm going to leave the constants out to the left factored out and do the evaluations of just the portion parentheses from 97 to 16. So 2 divides 162, getting us back to 81, times 3 gives us 1 over 243, I think. Sounds about right. Times, put in 97 to power 3/2 minus 16 to the power 3/2. And this would be the exact distance traveled by this proton going along the purple path here in units of, let's just call it femtometers, because that's a weird word. I guess we want to round this one to 3 decimal places, so let's do that as well. It wouldn't feel right to leave it as it stands, so we have 1 over 243, 97 power 3/2, minus 16 power 3/2 as well. And so the distance is, to 3 decimal places, 3.668 femtometers. So again, I'm not too sure if they really do this at CERN at the Large Hadron Collider, if this problem has any value, but it's cool to know if the particle is, or anything is given parametrically, you can track the distance traveled just by using the formulas here that we specified. Just calculate the x dt, dy dt, square them, sum them, square root them, and then you're on your way. Integrate that result. What, any last questions, folks, with that final problem there? Okay, well, we did it, folks. That's the last official question of the entire course. So that's kind of awesome in a way. All we're doing now is reviewing for the final exam at this point. And again, like I mentioned, as far as section 10.2 goes, I'm only going to ask one question. And you'll need to know how to calculate dx dt, dy dt. You'll notice that that's in a lot of these formulas, whether you're doing area, lengths, but you're also going to need to calculate d2y dx2. So if you can calculate the first and then the second derivative in this kind of way, like in example 4, then you're going to be in great shape. I'm not going to ask anything too wild. It'll be something very similar to these kinds of problems. Well, let's close this off. I'll get the results uploaded as usual. And now we're working on this document here. It's just like an ordinary set of lecture notes. You can find this document as a Word document and as a PDF under the blank lecture notes. It's way down, I think, on the bottom. Final exam review problems. I won't be uploading the results as we usually do for these kinds of things. Let me first get my window situated. So this is essentially just a bunch of problems, mostly in the order we did the course. But I found some places just injecting extra questions, so a little bit gets mixed up towards the middle. I feel like it's probably a good idea to just start at problem 1 and work our way all the way to the end as far as we can to problem number 29. That's a lot of them. And if we run out of questions, I can very easily come up with a whole lot more. So there's no worry about that. And again, if there's any questions that folks would like to ask while we're in the middle of these, please don't hesitate to interject. I'm very happy to go and sideline a problem that we finish off and work on a next one before coming back to the next problems. But so far, it looks like we're going to be integrating some stuff we're reviewing in chapter 7. We'll just go down the line on this document. First up is x cosecant squared x dx. You know, as we do this, I'll probably also include some screenshots of things you might want on your lecture, or excuse me, your exam notes for the final exam. And seeing this already, one of the big things that I would include for my notes on the final exam is this document. Go to section for integrating. A good section on that would be 7.5, strategy for integration. And in that section, you have a long list of really good stuff that you could take and just paste into or just write down if you prefer. If I can get a good screenshot of this. So here's a good list of things you might want to include on your notes. Let's just drop it right here. We'll refer to them as needed. So far that doesn't help us though. There's no x cosecant squared on these formulas up above. I don't think there's even, well, there's cosecant squared x, of course, but that doesn't help us whatsoever because x is multiplying this one. What we have to use now is integration by parts. So we'll start off with this table. If we can fill this out, then this is good partial credit already on this problem, and it gets us set up to finishing this off rapidly. We just need a good choice for you. Anyone recall what a good choice might be in this case? Absolutely. Usually if you see an X, that's almost a dead giveaway. Not always. So if you're not sure, this is a great acronym. Once I get the acronym right, LIATE for picking the functions. A stands for algebraic and it refers to X. But really the better way to think about this in a certain sense is X is the best choice here because when you go to find the differential of this equation, it becomes just dx. Complexity goes way down, so that's what you want to see. You wouldn't want to pick something that becomes more complicated on this line after you differentiate. So that leaves behind VB is everything else, cosecant squared x dx. And we do have an antiderivative of that. It's up there on the table. This one is negative cotangent x. So that's our setup. And back down here, if you write out this, uv minus the integral b du, that gets us started. All we're doing now is, the official method is called plug and chunk now at this point. Pick your u, throw that one in. Go to your v, that's negative cotangent x. I'll squeeze a negative right in the front because I forgot it. Minus the integral of v, here's another negative sign. I'm going to put the extra negative here, forcing it to be positive. Cotangent x dx. So that's what it settles to at this stage here. We can get an antiderivative of cotangent, we're on our way. So this equals negative x cotangent x, and let's see, antiderivative of a cotangent. A little foggy on that one, but I'm pretty sure it's a natural log, absolute value, and it's either sine or cosecant. Anyone happen to remember? It's a u substitution if you forget and don't have the note, but let me just throw it in here. Here's my best guess. I believe that one's a sine x, but if you haven't used that formula in a number of weeks, that becomes foggy. So let's double check. Where was I looking at? Cotangent x, natural log of the absolute value of sine x. Tangent is the weird one because it's secant instead of cosine. So that's the value of this table right here already. If you feel like you're kind of foggy on some of these, honestly, just writing them down once, and if you never even look at it again on your final exam, that's helping with learning already. And the problem's done. We've completed it by integration by parts. It goes really fast when we're familiar with it, and we know all of our antiderivatives as they come up. Any questions with that one there, folks? Okay, moving down the line, we have a trigonometric integral coming up next. These ones are always u substitution, but they're a clever kind of u substitution where you also have to use a trigonometric identity to make everything come out just right. I think oftentimes the best way to think about these is trial and error is a good call. So if I just see a random tangent squared secant power 4, usually my thought is it would be convenient for u to be secant power 4. It has the highest power. It's not a guarantee it'll work, so let's try it out. U equals secant power 4 of x. Excuse me, it's just secant x rather. Don't take the whole power, just the function. Then you check out the differential. D would be secant x, tangent x, dx. Already that tells us this won't work. Anyone see the reasoning why this fails? Yeah, that's the trouble here. If that was power 3, you know what? We'd be in business. But because it's power 1, this is our best attempt to force it to work. We would write, let's see, 10x secant power 4 of x. Or hang on, we have to go secant power 3 of x, because we need to leave off one power of each, secant x, tangent x, dx. So this one's no problem. That's u cubed. This is no problem either. That's du. That's the problem. What to do with tangent x? Again, if the power was just right, power 3, it would be no issue. So this tells us this try fails. And if this was a real final exam, one thing you could do for time strategy, time management, just move on to a different problem right at this stage. That way, when you come back to this, even if you don't have enough time to launch into a whole new strategy, this is already partial credit, a lot of it in its own right. So it's not a bad idea to sometimes leave off a problem, let your subconscious work on it while you try other problems. But if it's a trigonometric integral and secant didn't work, you just go to the next, try tangent this time. U equals tangent x. Excitingly, we'll get to explain why does tangent x work, whereas secant x failed. It's all about the differential. Differential is derivative of tangent, which is secant squared, dx. That means over here, well, we'll have u squared for tangent squared. We need to give away secant squared, so the integral looks like this now. Tangent squared x, secant squared x, times secant squared x, dx. So this part right here is du, so that's good. This part right here is u squared, even better. And because this is an even power, that's even better. We can now say secant squared of x is by identity tangent squared of x plus 1, which is by our substitution, u squared plus 1. So this whole thing right here turns into a u squared plus 1, and that means, well, it's almost silly to have written all these, because that's what we're integrating. The integration will work on this one method. So this works. Well, all we have to do is run through the method now. In this position, it's antiderivative of u squared times u squared plus 1 times du. So we reduced a calculus 2 integral back to calculus 1. And that's pretty much the strategy of all the problems in chapter 7. Try to reduce the complexity some way, somehow. So now it's an antiderivative of u power 4 plus u squared du. Antiderivatives go a fifth. This is u power 5. But you know, if you've done these a lot and you feel like you want a shortcut, you already know it's u. If you put in tangent power 5 at this step, that's a pretty appropriate shortcut people start taking more and more as you do these problems. But I'll write it out for the paper trail. So it's 1/5 u power 5 plus 1/3 u power 3 plus a constant. That's a weird looking 3, but I think we can let that one stand. So this turns into a fifth tangent power 5x plus a third tangent power 3 of x plus a constant. At this stage, our work is complete on this one. So integration by parts is kind of a nicer problem when you take a look at this one. These are a little bit tougher sometimes. And sometimes it has to do with just the finicky way you pick the u substitution. I think the bigger thing that makes these challenging is you have to be familiar with your trigonometric identities. So this is good for notes. But you will
Quick
also,
question.
go ahead.
Sorry. Could you reduce the u4 plus u squared even more and just combine them before you did the integral?
Well, they aren't like terms, so we couldn't combine them by addition. If we were to factor, we'd be back to this stage right here. So actually right here, this is the best format of the answer for finding an
Okay.
antiderivative at that step. Other questions at the moment? Okay, so again, the thing that made this one challenging, and probably the one down below challenging as well, is the random trigonometric integrals are going to come up. But instead of actually putting these down in your notes individually, here's what I would suggest. Let's go back to section 7.3, trigonometric substitution, because this table is brilliant the more and more you look at it. It has the things you don't want to see in your integrals. It has the substitutions that eliminates them. It gives you domains that tells you when the substitutions are valid. We focus on these a little bit less, but it's good to have that information. And it gives you all the nice trigonometric identities we've been looking at. We just used this one, for example. So I would highly suggest making this a part of your final exam notes right here. Let's put it on the document as well. And let's put it right here ahead of problem number 2. Looks like that's when it comes up for a trigonometric integral or substitution. Let me erase that since, again, I think the better candidate is this whole table right here. Well, any other questions so far, folks, before we jump into another? Okay, well, this next integral is pretty much the same strategy as the one above. We need to find a U substitution that works and just run with it. Any volunteers for something to try? It's like a USB. It's either going to be one or the other. You could just try to pick one and ram it through. If not, try the other. Cosine? Awesome. I usually try that strategy out when I see the highest power. Doesn't always work like on this one. So let's give it a try here. U is cosine t. This looks like it should work because of the odd power sign that makes it work. But let's keep on going. If u is cosine t, then its differential is negative sine t dt. So that means we can come back here and write negative du is sine t dt. And this is a good stage to come back to the integral and just start reorganizing what we're about to do. So right where you see that sine cubed, we need to give off one factor. So it's now sine squared of t times cosine power 6 of t. I put this little multiplication right here to kind of indicate beyond that is where the differential is going to go. So it's has to involve sine because we split off one power. We need a dt on there. So that tells us so far, this is going to be negative du. This part is u power 6. And we just need an expression for sine squared t. Scrolling down just a bit. Oh, shoot. Hang on, let me control C that. Scrolling down a bit in this way. This is the identity that we want to make use of right down here, essentially. We're solving for sine squared and turning it all around. So we can say sine squared t is 1 minus cosine squared t. Because u is cosine t in this problem, it turns into 1 minus u squared. So right up here, we have a 1 minus u squared. We're now done with this table right here. Seems to be like some weird digital ink on that. There we go. Thought it was on the actual monitor screen. So now with our setup, this becomes that negative sign in front. Integrate u power 6 times 1 minus u squared. So it's going to be u power 6 minus u power 8 du. So that's our integral to calculate on this one. And just like before, we're pretty much home free on this one. We'll go minus. It'll be a 7th u power 7 minus a 9th u power 9. And in the constant, might as well just wipe out these parentheses and distribute in the negative sign. We get negative of 7th. U is cosine, so cosine power 7 plus a 9th cosine power 9 of t plus our arbitrary constant of integration. So we did it, folks. That's how a trig one would go down. And again, these are both pretty similar kinds of problems, the last one and this one here. Any questions at all solving this one? This is, I think, at this point, something like week 2, midway week 2 in calculus. When we get to the next problem, that's actually still week 1. This one looks like it's integration by parts out of nowhere. I guess this is a good reminder that the problems are not necessarily in order on the real final exam. I didn't try to mix them up or anything like that, but when I wrote the final exam, sometimes one page just doesn't fit too much, so I rearranged a smaller problem to fit with a larger looking problem. So it's mixed up just a little bit, nothing too major. And this one is definitely kind of out of order. This one's integration by parts again. So let's set up the table. U equals dv equals du equals and v equals. Now, if we copy the same strategy as before and pick x power 4 for our u, this actually fails. Well, it fails in a way that is not so nice to really spot right away. Let me show you what I mean. I'm going to put in x power 4 here and delete it in a moment. So this is just a trial run. Nothing stops us from picking x power 4. The differential is 4 x cubed dx. Now over here, we have to put natural log x dx. This is where a really common mistake comes in. Oftentimes when people see a natural log x for your dv, your differential equation, it's tempting to put a 1 over x here. But this is a major mistake. V is not a derivative. In fact, V is the antiderivative of dv dx. What this implies is you're forming the antiderivative. And so this would be something nasty like x natural log x minus x. In fact, it takes integration by parts alone to come up with that. And this is not reducing the complexity of the problem at all. So watch out for these kinds of things. This is where the acronym LIATE, all the way back from section 7.1, actually helps out quite a bit for this problem. Let's backtrack off these. Let's start with this. What this is saying is, if you find a logarithmic function or an inverse function, the logarithm is inverse to e to the power of x, so there's kind of a tie there. This is not a perfect acronym. But if you see a natural logarithm, really good call to just plug it in right here. Because now you're not taking the antiderivative of the natural log x, you're differentiating it, forming this differential, and it's correct at this stage. All that's left now is x power 4 dx, but don't forget you're integrating to find v, so this becomes a fifth x power 5. So that's the table that's going to make everything we want to happen actually happen on this problem here. So writing it out, we're going to do uv minus the integral v du. So now we're just plugging things in. U to v is really just multiplying this way. So that's the uv part, natural log x times a fifth x power 5. Let me put this in first. That just seems to read better if you put the natural log x last. Then next it's multiplying here to here for the last part. So minus the integral of v. V is a fifth x power 5 times du, which is 1 over x dx. I think a lot of times people simplify this at this stage. So if you didn't write this all in, you just gave me a fifth x power 4, that'd be a pretty reasonable shortcut. So we have one last integral to go. We're looking at a fifth x power 5 natural log x minus a fifth antiderivative of x power 4 dx. So this all becomes, after solving this one here, a fifth x power 5 natural log x minus a 25th x power 5 plus a constant. So my claim is, if you differentiate all of this stuff here and carefully maneuver the product rule, you'll get that in the very end. Well, any questions, folks, on our second integration by parts? Okay, Ed, here's something that I sometimes see on a final exam that leaves a lot of points on the table, potentially. Sometimes people are pretty fast at calculating these kinds of things. So if you find that there's additional time left over on the final exam, maybe you've got 20 minutes or something like that, go back to each one of your integral problems and do this. Maybe on the margin, maybe using your scratch paper. If you take a fifth x power 5 natural log x minus a 25th x power 5, it's kind of silly putting in the constant because it'll go to 0 in the derivative. But if you differentiate all this, it takes some time, but it could be well worth it to see if you get back to here. This could spot a mistake potentially. Let's work it out just to emphasize this is a pretty decent test-taking strategy all on its own. For differentiating all of that, we start with the constant multiple rule. A fifth stays right where it is. I'm going to go here, apply the product rule in that group that you see. The way I usually differentiate is just differentiate the first term. 5x power 4, copy natural log x, plus, now I'm going to copy the first term, differentiate the second term, giving a 1 over x. So that's the product rule applied to this portion right here. Going up to this, when we differentiate, 5 comes down, so we get negative 1/5, x power 4, and it's an arbitrary constant, but it's still a constant. It dies upon differentiation. So distributing the fifth through, we have x power 4 natural log x plus a fifth x power 4 when we consolidate those terms. Then it's minus a fifth x power 4. And this gives us x power 4 natural log x. We compare way at the top here. We have the same exact integrand. That means we did it. It was the right problem and we didn't have to check it. We had the right answer. But it's so easy to make a simplest mistake, like forgetting that that should have been a 25th instead of a fifth, that again, it's worth taking that extra time if you have it. Well, that was the check. Any questions, folks, with the process or the check? Okay, let's try off the next one then. This one looks like it's a trigonometric substitution problem for sure. Not necessarily for sure. Sometimes a very clever use of a U substitution can transform this into something more manageable. But usually that takes a lot of extra creativity. It'd be an ad hoc U substitution new to every one of these kinds of problems. I think a lot of people would be more successful picking one of these. Anyone see which option we should pick? Option 1, 2, or 3?
2.
Good call. The giveaway is option 2 is the only one that handles plus in the middle. So we've got to go that route. And this is a good enough process in its own right. We should take our time with this. So here is what I would consider step 1 in this process. We're picking this right here. That means x is a tangent theta, and we'll write out x equals, in place of that a right here, it's going to be a 4, rather a 2 to the power of 2. So essentially, whatever is here is a square, that's 2 squared, comes back over here as just a 2. You know what? Thinking about, maybe the best way to think about this is square root the number here, and you've got the right value. That's probably a better way to think about it. X is 2 tangent theta. So once you have your substitution, in step 2, you want to very carefully calculate the differential. We're working on that part of the integration, or this part of the integral. Dx is going to become 2 secant squared theta. And don't forget, it needs a d theta to fully transform this into the right integral. Now, next step 3. We're working with everything else that's left over. X cubed is not bad. We're just cubing this, so usually we don't emphasize that as much. We do emphasize that. Let's work this one out carefully. Root 4 plus x squared becomes the square root of 4 plus x squared is the square of this expression, so it's 4 tangent squared theta. We pick the 2 that you see right here in such the way that when you square it, you have a match of these 2 integers. That's what's going to allow this identity up here to work for us. So factor out 4 outside the square root. It looks like this algebraically. Leaves behind 1 plus tangent squared theta. So now we have 2 root secant squared theta. And then finally, this is how the rest of the information comes together. This domain is selected in such a way to ensure that when we come here and take the square root, absolute value does not occur. We really get just secant theta because secant is positive on that domain since cosine is. So we get here 2 cosine theta. So that's going to go into that location. And this is what I would consider step 4. Now we transform the whole entire integral. So this turns into integrate. First x cubed up above is going to be 2 cubed, so 8. Tangent cubed theta. Down below, we found that the expression here became 2 cosine theta. Excuse me, that's not quite right, is it? That should be 2.
Yeah, I was just about to say, how do we get cosine theta?
I was just
Is that
thinking
secant theta?
Yeah, the power here should have canceled the 2. Should have just been a secant theta. Sorry for that weird typo there. So 2 secant theta goes down below. That looks a little bit more normal. Okay, off to back on track. The last part, dx, because we wrote out that differential, all we're doing is plugging it in, times 2 secant squared theta d theta. Now we have to integrate it. So this could be an adventure in its own right. This is now turning into, we could factor 8 outside the integral, secants cancel. And now it's tangent cubed theta, secant theta, d theta. If we can integrate that thing, we're all set. So now we need to come up with another u substitution. And this would be step 5 now. These are pretty long problems whenever a trigonometric substitution comes into play. This is just like the second example that we did for the day. It's an ordinary trigonometric integral. We pick u as tangent. Its differential is secant squared. That doesn't look helpful. So we should pick u equals secant. The good thing about this is its differential is secant theta, tangent theta, d theta. That means from here, we're factoring away 1 power, leaving behind tangent squared, theta. The same table up above tells us that tangent squared theta is secant squared theta minus 1. The visual on that is, you're just going, oh, it's literally what they wrote in, forgot. So it's just that right there. Secant squared theta minus 1. So that means it becomes u squared minus 1. And we should be in good shape here. Let's do one optional step just to organize. That's, I think, what we did every single time we did one of these problems. But if it doesn't look too valuable to you, that's a step worthy of skipping. So tangent cubed, I'm going to rewrite as tangent squared, theta, then go times secant theta, tangent theta, d theta. So all of this stuff here is now du, and this is now u squared minus 1 from this segment of step 5. So we're ready to integrate this thing. Some more space than I realized. Let's just take the whole page. So once we go to integrate this thing, this turns into 8 antiderivative of u squared minus 1 du. So now we've got 8 times a third u cubed minus u plus a constant. An important feature about these kinds of problems is that knowing how to undo the substitutions is about equally important as knowing how to do them in the first place. It's not like you'd lose half credit if you stopped right here, but it could be a significant amount of points. This is an 8-point question. It'd probably be 2 to 3 points to finalize undoing all the substitutions. So this is what I would call step 6 next. We're undoing the first substitution where u is secant theta. I'm running out of colors, but I guess we can still do this. So undoing those 2 substitutions will give us 8 a third secant cubed theta minus secant theta plus a constant. So that's step 6. We undid that substitution. This takes us to step 7 because there's one last substitution to undo. The original integral was in variable x. So we have to go all the way to step 1. It wraps back in on itself. Use that to undo our substitution. Let's carry it down. If x equals 2 tangent theta, this then implies tangent theta equals x divided by 2, which is the opposite side of theta divided by the adjacent side of theta. So out of nowhere, we do right triangle trigonometry on this problem. Feels like just a huge review of a lot of mathematics. The right triangle trigonometry can be pretty basic. My triangles always look exactly the same, even though the proportions might not be accurate. I always plug theta here, and by opposite, we mean x goes in this location. By adjacent, 2 goes here. Apply Pythagorean's theorem, and this hypotenuse is the square root of the square of the sides. So 4 plus x squared. Once you get to this stage, you should do another check in the problem, because 4 plus x squared right here has to match up exactly with 4 plus x squared up here, which was the reason we did the trig substitution to begin with. So if that matches up, that's a really great consistency check on your work. And here's the final step. I guess this is really still step 7, undoing the last substitution. We have 8 times a third. We need to come up with secant theta. So we come over here and write secant theta is the hypotenuse divided by the adjacent side. So it's the root 4 plus x squared divided by 2. So that whole thing, root 4 plus x squared divided by 2, goes here and we cube it. That's a bit annoying, but if you're raising a square root to power 3, all that happens is that 4 plus x squared becomes power 3/2. I think that's the best way to write it in. We also cube the denominator, so that 2 turns into an 8. Minus, then secant theta just comes up again, so root 4 plus x squared over 2 plus a constant. And, depending on what you do to this, it's still not quite done, because if you distribute the 8 through, it can cancel. If you don't distribute the 8 through, we still should simplify what's going on here by the red dot. I'll leave this way, 8 factored out. Our official answer would become 4 plus x squared to the power 3/2 divide by 24 minus root 4 plus x squared divide by 2 plus a constant. So my claim is the antiderivative of this really simple looking integrand, x cubed divided by root 4 plus x squared, is that gigantic mess. Integration is just weird in that kind of sense. And what's kind of awful about these problems is I would encourage you not to differentiate it on the final exam, because sometimes the check on that is a lot more effort than is really even necessary. Maybe it wouldn't be too bad. That's not too much of a chain rule on this one. But sometimes these become just not very friendly to even check in the first place. But this is what a more difficult looking trigonometric substitution would look like. I think on a real final exam, I would probably select a problem that doesn't have quite as many steps. So think of this one as just a gigantic review problem. We did multiple sections in one. Any questions whatsoever, folks, with the full rundown on this one? Okay, I think we have time for one more. Let's see what we can get going.
How many points do I lose if I don't do step 7?
Step 7, I would say, let's imagine it's an 8-point problem. I would probably assign about 5 points to get to this stage right here. 1 point for this one because it's just undoing an ordinary U substitution. It's not too major. But probably a couple points for this because it was a major part of the method, knowing how to navigate through that last part. So on a real final exam, it's not worth a whole lot, but it's one of those places you wouldn't necessarily want to get nickel and dimed on with points if you can find the time to do that last part. Any other questions so far? Okay. Well, I was looking at a question we can do in 7 minutes, and I don't think it's that one. This one is partial fraction decomposition type of a question. So let's see if we can get another one going. That's an improper integral. Some of these are a little bit longer. You know, let's just stick to our guns. Let's try this one out. It splits into 2 parts naturally, so we can come back to it if we need to. Actually, let me change this one just a little bit. The way I wrote that question is slightly different how I wrote it on the final exam. So let me wrote it how it would look like as a real final exam question. X cubed plus X. We put that in red to just say we changed it out. This is a new problem now at this point. So if you saw this as a final exam question, I think this is a really tricky integral. U substitution won't work out unless there was a -3 right there. So it's so close, but it doesn't work. Oh no, that needs a little bit more actually for what's in the numerator. So this is one where we have to use partial fraction decomposition. But step 1 is to ensure the denominator must be factored. So that's the change I wanted to make on this question here, because I noticed on the real final exam, that's what we have to remember to do. So let's start off by rewriting x squared minus 3x plus 1 divided by x cubed plus x. So in this problem, we're not even worried about the integral first. The first thing we want to do is maneuver through the decomposition. So this becomes, let me drop it down the line, x squared minus 3x plus 1. We can factor out x from this expression and leave behind x squared plus 1. So this is where the problem started before we edited it. And down below, that is fully factored. X squared plus 1 is an irreducible quadratic. It means if you try to factor that thing, you'd have to use complex numbers. And that means this is case 3 for the partial fraction decomposition. I think my hand is getting tired at this point. So let's review how that case goes. The first thing we start with is each of the unique factors. This is x to degree 1, so we just write a over x, and then move on to the next. If this was x cubed instead, we would have had to write in plus b over x squared plus c over x cubed before we go on to the next factor. Then when we go to the factor x squared plus 1, because that one's irreducible at degree 2, anyone recall what happens to the numerator? Good call, absolutely. It has to be degree 1 now. So bx plus c, just as you said. One way to think about this is every term you put down is a rational function, but the degree of the numerator is exactly 1 less than, no, hang on, that's not quite true. I forget, different cases come up. That was almost true, but not if this was case 4 and that had a higher power. But if it's just x squared plus 1, it's the first time you wrote it down. Up above, it's a degree just 1 less. So that's step 1. And step 2 looks like we've done the decomposition. Let's call this whole step right here step 2. This whole step right here. So in the decomposition, next thing we do is we clear the denominators. So we're multiplying everything by x times x squared plus 1. On the left, you'll have x squared minus 3x plus 1. When you multiply it by that same quantity over here, you get a times x squared plus 1 plus, over here, this becomes bx plus c times just x. Does that make sense to folks visualizing it that way? Okay, well, next thing we need to do after clearing the denominator is find a way to solve for all three coefficients, A, B, and C. Let's see, we've got 2 minutes. This might be a good stopping point for us right here, but here's what I would suggest. Pick x equals 0. If you do that, you get 1 on the left-hand side equals, this just turns into A times 1. And this whole term is gone. So that's 1 down. Here's where it's going to take more than 2 minutes. We'll have to come back to this one. Next, when you pick x equals positive 1, you'll get an equation with 2 unknowns, B and C. That means you have to pick another value for x. You'll get another equation with 2 unknowns, and so we can solve both of those equations pretty rapidly on this problem. So I think that's a pretty good strategy for getting through this question here. For folks that like to use the method of equating coefficients, that would also work out pretty well as well. But sorry, folks, this was hard to find a problem that takes just 7 minutes to describe and solve the full process. So we'll come back to problem 3 on Wednesday's class. But as usual, I'd also be happy to start out with any questions folks would like to bring as well. They could be from anything whatsoever. Well, any last questions at all, folks, before we call it a night officially? Okay, well, thanks for your hard work all semester. This is week 15, so we're finally wrapping it up. Have a great one, and we'll come back to that part right here on the document on Wednesday's class.